Hello, welcome to this video on the mathematics of sound. So what I will try to do in this video is give you a short introduction on how you can describe sound mathematically. What is sound? How can you make sound visible? And with the mathematical description, I'm going to show you some fun experiments with actual sounds and what you can do with them if you have this mathematical description. So let's see, let's go to the slides and a short outline of the video. So first I'm going to talk a little bit on how you can make sound visible. Then I will be talking about music and pure tones. So pure tones are the building blocks of sound and music. And then I will do a fun experiment where you have a sound that sounds surprising, I would say, and that we can give an explanation for that using its mathematical description. So let's see. First of all, if you think about acoustics, about sound and musical instruments, the way you can describe that is by pressure waves. So if I'm talking, then my vocal cords make the pressure in the air vary. These pressure variations reach your eardrum, and your eardrum picks that up and translates it back in your mind to sound, to me speaking to you. So the mathematical description, a mathematical description of sound, is the pressure of the air, say at your eardrum, as a function of time. And all musical instruments in some way make air vibrate. So you can think of a string of a guitar, or a membrane, or maybe a tuning fork, or an organ as you find in church. And all of these instruments make air vibrate. Now, already many years ago, there was a German, Chladni, and what he did was try and make these vibrations visible. So what he did is try and make sound visible. So he took a metal plate, as you see here, fixed it in the middle here, and then he would make that plate vibrate using his violin bow. And then this plate starts vibrating, and if you pour a little bit of sand or salt or whatever on this plate, you will get interesting patterns. So that's what you already see here in this picture. You see that you have some patterns here, and I would like to talk a little bit more about that. So let us first look at the one-dimensional equivalent. The one-dimensional equivalent would be a guitar string. So what you see here is an experiment, and this is not a YouTube movie that I didn't make, but there is a link here below the movie. And what they do is they have a string and they make it vibrate. And as you know from physics in high school, so let me start the movie here. As you know, at certain frequencies, you get patterns there. So the simplest pattern is the two endpoints are fixed, and in the middle you have like a maximum sine type of wave. And then if you go to higher frequencies, you get two of these nodes. So nodes are points where the string does not move. So here you see that in the middle, there is a node, so the string does not move there. And here there is a node here, and there is another one here. And if you keep increasing the frequency, you will get more and more of these nodes. So that's points where the string does not move. 2D, you have something similar, because what happens in 2D is that you won't have single nodes, but you will have nodal lines. So these are drawings made by Chladni that he observed when he was making his metal plate vibrate with his violin bow. And for instance, in the first one, you see that here, this horizontal line and this vertical line, that are nodal lines, that are places where this plate is not vibrating. It's fixed there. And in the white part, so for instance here and here and here and at this place, there is maximum vibration. And if you put salt there or sand, then it moves away to the nodal lines. And by using different frequencies of the plate, you get different patterns. So here you see that the diagonals are nodal lines, and you see that going from left to right and from bottom to top, these patterns get more and more complicated. At higher frequencies, you will observe more complicated patterns of the nodal lines. Now, I also found a different movie on YouTube, which shows the kind of modern version of how you can do this experiment. So what you see here is also, well, there is a little bit of introduction here. They have a plate, which is also fixed, and then they use loudspeakers to make this plate vibrate. So what they do here is the setup, and you can see here on the left is the device that generates the frequencies, that generates the sound. Below here is a speaker, and you can observe, so this is the frequency, they start at 100 Hertz and they will make it go up. They pour some sugar, I guess it's on the plate, and the plate is fixed in the middle. So if we get to see the plate again in a second, the sound's not important here, there is some music in the background, but I just switch it off. So it's fixed here, and you see that at different frequencies, so here's the frequency that it currently has, you see that you get different patterns there. And indeed, the higher the frequency, the more complex these patterns get. So we already had 1000 Hertz, 1820 Hertz, and you see that you get these very nice patterns on the plate. Coincidentally, you can also compute these. So if you make a mathematical model of the plate, you can also compute where these nodal lines will occur. That goes beyond calculus, but if you're interested, I also teach a course in numerical linear algebra, and there I also explain briefly on how you can compute these, and I will compare the computations with the actual patterns, and you see that they match surprisingly well. So this goes on for a bit. If you want to see the rest of the movie, just click on the link that was there. Go back here for a sec, so you will see here. If you have the PDF, then you can read a little article on this and you will find more information. Yeah. So let's continue. So what we have is that sound can be described by a function of time, by vibrations in pressure. And the elementary thing that you have, the elementary building block of sound, is a tone. So what is a tone? Mathematically, a tone of F Hertz, so for instance 440 Hertz, that's a standard tone A that a tuning fork makes. If you have a function that is periodic, and I will explain in a bit what it is, with a frequency of F Hertz, that means that the signal repeats itself F times per second. Hertz is just per second. And it means that if you would draw the function as a function of time, that after a period of capital T, which is 1 over F, the function starts repeating itself. So you can draw a function and you just get copies of the same function. It repeats itself after a time of capital T. For instance, so the kind of elementary mathematical function that is periodic is the sine function or the cosine function. And if you have the sine, so A is called the amplitude, and that just tells you the largest and smallest value. So the largest value of this function is capital A, and the smallest here is minus A. Then on the horizontal axis is T. And if you have this function, so 2 times pi times F times T, then you will see that, for instance, if you pick a frequency of 1 Hertz, then if T goes from 0 to 1, you have one full sine, and then it starts repeating itself. So this is a pure tone of frequency little f, and this is the graph. And indeed what you see is here we have one sine, and then after a time of capital T, you just get a copy. So you get again the same sine function, then we end up at 2t, and then you see that we again get this. So let's just for fun listen to tone A. So A is 440 Hertz, produced by several sources. So what do I mean by sources? I'm going to let you hear my computer that can create this sound, which doesn't sound very nice. I have a tuning fork, a piano, and a human voice. So let's listen to the first instrument, and the first instrument is going to be the pure tone as generated by a computer. So you can just play a sine function with mathematical software, and I did that, and this is what you get. So it doesn't sound very nice, but you can hear that is a tone at this frequency. I'll play it once more. So let's go to the next instrument, and the next instrument is a tuning fork. So let's play the sound. And you probably know how a tuning fork works, so you strike it against something and then you put it on a desk or whatever to make that vibrate and create a sound. So first it's a bit soft, and then I put it on the desk or on the top of the piano, I think, and then you hear it again. So let's play it once more. So it sounds different, but what you see is here I plotted part of the function, and you see this is the perfect sine function. This is the tuning fork, which is pretty okay. So this is a small clip of the sound file where you see that per time period it repeats itself. So it's also a periodic function, approximately, right? If you look at the amplitudes here, you see that it's not perfect, but it's a good approximation. So let's go to the next instrument, which is the piano. And here you see that the shape of the graph has changed because there is this little thing here. And that means that we hear also higher frequency sounds together with the 440. But the whole function together has a frequency of 440 Hertz. So let's listen to it. And let's play that once more. And then finally, as the last instrument, let's listen to the human voice. And you see here that the graph is a lot wilder because there are many higher frequencies there too. You can imagine if you have a tone of 880 Hertz, then that will also repeat in 440, but you will get two copies in the same time period. So let's listen to this. And then once more. This is actually my wife you're listening to now. What you see here is that we have 4 different instruments, and they all produce sounds of 440 Hertz. The graphs look different, but what is the same in all of them is that in a certain time period, you have some difficult graph that just repeats itself, that has copies of itself. And that is what characterizes a tone of 440 Hertz. Now, in general, if you hear more than one tone at the same time, so say we combine 2 tones, then to the human ear, what sounds nice, what sounds pleasant, is if you have 2 tones with 2 frequencies, say F1 and F2, if you divide them a simple fraction, then it sounds nice. So for instance, if you have a tone of 440 Hertz plus twice that, so 880, 440 plus 880, that sounds nice. Or if you divide the frequencies F1 over F2 and you have 2 over 3, that's called a fifth in music, and then you have a fourth, a major third, minor third, all simple ratios. So as an example where you see that this is true, where you hear that this is true better, I'm going to play a tone with a frequency of 440, so that's the A we just heard, plus 1 of 880. Now if you make a plot, then you get the graph that you see over here. So indeed, it repeats itself. And if you listen to that, it should sound pleasant. Well, maybe not terribly pleasant because this is a computer generating that noise. So let me play that once more, and I lowered the volume a little bit because it was a bit loud. So let me play that once again. Okay. So it is computer generating. It doesn't sound terribly nice, but it's okay-ish. If you have a more difficult fraction, so I'm going to combine now two tones with two frequencies that are not a simple fraction if you divide them. So let's see, the example that I have here is that I take, well, the same tone of 440, but now I'm going to combine it with a tone of 450 Hertz. So if you would divide these frequencies, you get 44 over 45. That is not a simple fraction. Also, if you plot them together, you see something funny happening here. Because this graph looks all red, what really happens is that, for instance, if you would look in this region here, is that the graph jumps up, down, up, down, up, down all the time, which is why this is like solid red if you plot it. So we get something strange here. We see basically a combination of a low frequency. If I start here at the top and I follow the graph here, then you see I can go down and all the way here and then up again. And then I have one cycle of the sine function. But you see that you have there a period, so a time period, from 0.2 to 0.4. So let's see what we have here. The frequencies are not so simple. We get a graph with the high and the low frequency. So the low frequency is the frequency corresponding to 0.2 seconds. So that's 1 over 0.2 is 5 Hertz. And there is a high frequency. I cannot see that frequency, but I just know it happens because I see a solid red region there. So we see a low frequency with a frequency of 5 Hertz. And if you listen to this, let's do that. And let's play it once more. So what you hear is that the sound gets louder, softer, louder, softer, louder, softer. So that's really strange. That's not what you would expect if you play a tone of 440 plus something close to that. Now, the fun thing is that we can explain this using mathematics. So let's do that. So we have these two tones. This is the same as from the previous graph. And now I'm going to use some trigonometry. So we will see this in future videos. For now, I'm just going to use it. So you can prove that the cosine of alpha plus beta, you can write that as cosine alpha cosine beta minus sine alpha sine beta. If I then replace beta with minus beta, then here you still have cosine beta because the cosine of minus beta equals the cosine of beta. The minus sign becomes a plus because if you replace this thing with minus beta, then you get an additional minus sign. I'm doing this very quickly, but this is just for the experiment that I want to explain this. And we'll get into these trigonometry rules, so then we'll do it more slowly. Now, if I add these two formulas together, so on the left, I add these two cosines. On the right, you see that these signs, they drop out because this one has a minus, this one has a plus. So if I add the two equations together, they drop out. Now, again, a bit fast. Normally I would do that slower, but this is just to explain the phenomenon. I'm going to call this alpha plus beta. I'm going to call that gamma. Alpha minus beta, I'm going to call delta. So then we get cosine gamma plus cosine delta. If you do that, again, take some scratch paper, you will see that. Then you can write alpha in terms of gamma and delta as this, beta as this. And now, so this is just a very quick derivation of this trigonometry rule. You can rewrite our signal that we were listening to by using this rule here. And I can rewrite it as what we have here. And this explains precisely what we hear. Because this tells you that we hear basically a tone with frequency 445 Hertz. And this factor in front of it, it is a bit like an amplitude, but still it depends on time, so I'm a bit cheating here. But this tells you why you have a frequency of 5 Hertz in there and why it gets louder and softer again. So that's done by this cosine function here. So much for the experiment. Just showing you that you can describe sound using mathematics and typically using sines or cosines, and that you can explain some of the phenomena that you see there. So let's wrap up this video. What we have seen is that you can make sound visible using these plates and pouring sand on them. You can describe sound mathematically using periodic functions. And finally, you hear beats when you play two tones that have frequencies that are close together, not a simple fraction. And we have seen how you can explain that. That wraps it up for this video, and I look forward to seeing you in the next one.